Thank you. So I will be giving the last DARPA Provers related presentation. Just my disclaimer is that I am a systems engineer, and a lot of this is focused on formal methods, so please be kind to me. As you know, many seL4 based systems have high assurance requirements. Sometimes you can just rely on just the isolation guarantees it provides. However, sometimes you need to extend that into user space applications. There were a good number of talks yesterday about how we can start, verifying applications written on top of seL4 based systems. So when I was looking at that and thinking how to increase user application confidence, I think there's kind of like 3 steps you can take. One is to utilize memory safe and type safe languages. Next is testing your applications thoroughly, and finally, formally verifying your applications. Obviously, if you're doing the last one, you don't care so much about memory safety because you can prove it through your formal verification. However, I do think by layering the approaches, it makes it more accessible to people coming from a background like me where we don't have a PhD in formal verification. And so just a quick little refresher on the inspected tools. I mainly used HAMR and Veris for this work. And so HAMR was the system modeling and code generation tool that John talked about at his keynote yesterday. And this tool allows us to automate and connect system architecture to the application implementation. And I'll discuss a little bit on examples of how I did that in my system. And then Veris is a tool for verifying the correctness of code written in Rust. And the use of HAMR takes the architectural contracts, and those are used to generate the application level contracts in Veris. So then the user can go and use those as their post conditions for kind of their overall assurance story within the component itself. And then also the architectural contracts can be used to generate executable versions of the contracts. And then these can be used, that's executable Rust code, and these can be used to enable property-based testing to make it a bit quicker and easier to implement unit tests. So my use case architecture, what I wanted to show was a very common use case, which is you have some legacy code or you have people creating applications and they don't really think about security. It's more of an afterthought. So maybe halfway, 3/4 through the program, you actually start trying to address your security requirements. One way you could do that in the system on the left is that you can implement, say, a firewall within Linux. However, if you need like guarantees and confidence on that, good luck verifying the Linux firewall, right? You're not going to do it because of its interconnected nature. So the idea then is to use seL4 and create protection domains and separate them out. And so we've ended up with a system on the right where we have 2 unidirectional firewalls in between the VM as well as a low-level Ethernet driver. And this gives a nice clear separation between application development and security features. So the low-level Ethernet driver, this was actually originally developed without the inspected tools, but then were eventually ported into the generated architecture. It was implemented in Rust, and this mostly gives us memory safety. However, even in my manually written code, I needed a number of unsafe blocks. They're basically all just pointer arithmetic and dereferences related to MMIO and DMA regions. Generally, the way you handle that in Rust is you add a comment to an unsafe block and say why you're not creating undefined behavior. Eventually, it would be nice to be able to use Veris to formally show that instead of just writing a comment. One thing I was able to do was utilize the seL4 foundation libraries as well as example applications to reduce my effort in development, which was quite helpful. So Microkit libraries were utilized that provided things like convenient macros to translate the memory region symbols that are provided by the Microkit system file into mutable non-null pointers that I'm able to use in my application. And then the use of traits from the foundation libraries and third-party libraries, such as like small TCP, which is a common Ethernet stack, allows for standardized interfaces as well as the use of certain already implemented features. So there's some constructs that Nick wrote in the libraries where if you write your driver to have the traits, then you can get the notify function for free, basically. All you have to do is initialize your structure, and then you get a handler automatically. And then this application was quite difficult to test because it's mainly interacting with hardware. And by test, I mean more in the unit test case. And then continuing development was working on the firewalls. These were developed with the Inspector tools. So they were implemented in Rust within the HAMR generated architecture. They have very few dependencies and no manually written unsafe code. So this gave us a pretty good baseline confidence through memory and type safety. And then I also implemented manual unit tests, which gave me about 95% code coverage. Manually implementing them has some downsides. There's no real traceability from the unit tests to the requirements. And then also it required a decent amount of function mocking and stubbing on my interfaces for where I actually get and put data. However, because of all of these things, it was actually a really good initial target for verification. And so first, we need to come up with a verification approach. So there are actually different policies for data flowing into the VM versus data flowing out of the VM. And so we took that approach of implementing them as two separate components. And then the way it was implemented, I was actually able to use the same library for parsing the Ethernet frame into a type that was useful for the policy. In my requirements, I relate the policy to each relevant byte in an Ethernet frame, and so this kind of allows us to reason about the policy in relation to the frame as a whole. You can see that in the example on the requirement on the right there, and we'll kind of use that as a reference as I drill down into what my verification looks like. And I was able to write architectural contracts which essentially codify these natural language requirements into the Gumbo language. And I'll also note that my requirements through all this work went through kind of a formalization process where I significantly improved the specification within the requirements. My first pass at this was quite underspecified and just said, you'll allow a valid UDP port message through, and that kind of assumes the developer knows things about the specification in relation to the Ethernet frame. And by specifying it this way, it'll match up much more closely to what my specification actually looks like. And so as I started writing guarantee contract clauses. You can see kind of in reference to whether data is available, that and what that type of packet looks like, whether it's allowed out or not. And so, you know, if we take a look at that example of the UDP one, you can see I have a guarantee contract clause per requirement, which gives us a really nice traceability mapping, and you know, kind of starts to match what that says as you drill down. So if we look at that valid IDP UDP port spec function, you can see it looks very similar. That you know, the frame has a well-formed ETH header, the Ethernet type is IPv4, IPv4 packet is well-formed, yada, yada, yada. And if you look down in the requirement, then I kind of start defining what each of those things means. So it matches up quite well between the natural language requirement and the specification. And so drilling down just a little bit more, the well-formed Ethernet header is kind of two conditions, which is that you have a valid ether type and you have a valid frame destination, which is just that the frame destination can't be all zeros, and then it's one of these known byte patterns for IPv4, IPv6, or ARP. And so you then, those are all at the architectural level. Currently, those are written, in the AADL model. So they are associated with the model, which is used to do code generation as well as Verus spec generation. And that gives you the skeleton, including the spec skeleton. And so all these should look pretty similar already, which is that we have these guarantee contracts are now post conditions in Verus for my time triggered function, which is basically which gets called on at the beginning of a time slice for my protection domain. And then even the spec functions get generated into Verus as well. So once you define them once in the Gumbo contract language at the architectural level, you can reuse them in your component level verification without needing to necessarily rewrite them. And so I want to go through a little bit each of the pieces that I verified, starting with the frame parser library that both of my firewalls rely upon. A big chunk of the verification was done here. And essentially what I'm doing is just relating, I have this ETH frame type defined, and I'm relating the input frame versus what you expect to get out of the function. So in the case of our UDP frame here, we can equate an input valid UDP frame as a result that is UDP. And a valid UDP frame also implies that the port bytes match. So again, this should look familiar as the spec function, similar to the spec function that we were already looking at. And then these result ones, they take in the result and you're just checking, okay, did it pass me back something valid? If it did, is its ether type IPv4? If that's true, is its protocol UDP, right? And then, so that function is going to call on a number of different types of headers and chunks of the packet, so it'll take sub-slices of the Ethernet frame, and then start parsing each subsection, and then figuring out whether it's valid or not, and kind of constructing and building up your type that you're going to use for verifying your policy. And so, this is the first piece, the Ethernet header, and basically what we're checking here is whether what ether type is being returned. So still we're equating the frame values to the type returned, and you can kind of just see it keeps drilling down and more into sub-slices and kind of makes it more abstracted, but eventually you end up calling this where it's just checking those types and returning whether it's valid or not. If it's anything other than one of the ones we expect, it returns an error, which gets cast to a none here, which means anytime you have a malformed packet, it's going to eventually be returned as a none somewhere, and that gets propagated up. And so for all the different types of packets, all the pieces of the Ethernet frame that we care about for our policy, it basically takes that same approach as it goes down. And so then if we look at our specific implementation for, say, for the RX firewall, at the very high level, what it's doing here is just checking if it's received some data in on its input port, then it's going to get the frame packet. And if that is a valid frame, then it's going to send it through the can send packet function, which is essentially the overall policy. And if that's valid, then it will put it on the output port. And so when looking at the get frame packet, you can see how we relate. I think probably the coolest part here is that through Varus, we can actually export not just executable functions, but we can export the specification functions. So my functions on the get frame packet, my post conditions, can relate the generated Varus specifications that came from the contracts to the ones provided by the firewall core parser. And so, for all of these statements, once I had the shared library completed, I didn't need to write any more spec functions there. And then once it calls the can send packet, you can see here in our post conditions really what the policy is, which is that if the packet is ARP, if the packet is a whitelisted TCP packet, or if the packet is a whitelisted UDP packet, then you'll be able to send it. And what it does for looking at the UDP and TCP packets is it calls this UDP port allowed function. And these packet is whitelisted spec functions are just checking, okay, is it IPv4, is the protocol UDP, and then is it on an allowed port? Oops. And so this port allowed function, this was probably one of the more complicated things I had to do, which is where I actually had to do loop invariance. That was interesting in a learning experience. But one thing to note is because Varus doesn't have support for certain standard libraries yet, not everything in the standard library, as well as like certain type methods, that there's some areas where your code needs to end up a little bit more complicated to actually support verification. So, when I originally wrote this, the port allowed function was literally, it looked just like the spec function, right? Because there's a contains method on the slice, but because that wasn't already verified through the Varus libraries, I had to do that manually myself. And so looking at the TX firewall, the overall, like high-level implementation of the firewall on the inputs and the outputs of the ports are almost exactly the same. The only difference is that the driver needs to understand the size of the packet when it sends it out. So instead of just sending the frame through, we also send a size. But all the other function calls are basically exactly the same. The get frame packet, in this case, the code is exactly the same, the executable code. However, we care about different things. So we use different post conditions here, which is just that we're checking if it's ARP or we're checking if it's IPv4, because this side is a little bit less restrictive. And then our can send packet, here you can kind of see what the policy looks like again, which is just if it's ARP or if it's IPv4, then you're going to be able to send it through. We use an option here because we can either provide a wrapped value or a none to say whether it's valid, and then utilize the returned value, which is that size that needs to be propagated through to the driver. And so for ARP, that's a hard-coded 64, and then for IPv4, we have to add these. And So our verification results, I would say probably due to the significant unit testing that I did before verification, we really only revealed one new bug. That bug was a potential overflow in that addition of the IPv4 packet size, because that was technically allowing an unbounded U16. And so this resulted in a change to our requirements, our specification, and the code to now limit this size and allow verification. I spent 94 hours on the verification effort. 6 of those were paired programming with a formal methods expert from Collins. And then also an initial unrefined version of the Gumbo contracts and the kind of verification approach were provided by KSU. I think both of these pieces were quite invaluable for me for getting started. I wasn't quite sure on my own without the proper training of kind of like how to even approach the problem. However, I do think things like more tutorials and more examples might help people kind of start getting in the mindset of what are the types of things you need to do to kind of solve these verification problems even without like full training. Again, just mentioning I had no formal methods experience prior to this. And as I said, you know, there's some deficiencies still that are being worked on. Some code I need to make more complicated because Verus did not already support proofs for some standard library calls. And in some other cases too, like I had to change a function because they don't support bit shifting, which I think is maybe a difficulty with theorem provers, but obviously don't quote me on that. And then yet another approach that we took was the property-based testing, which is a nice alternative to handwritten unit tests. And so, like I stated, HAMR generates executable Rust code from the specification for the purposes of property-based testing. It took me about 12 hours of effort to write input array generation strategies to kind of coerce the frames into usable values for testing. That's pretty low effort. However, I think it's probably lower than average because that functionality from HAMR wasn't available to me until I had already done the verification, which means I already trusted my spec, I already trusted my code, and I already understood kind of the whole system really well. So, you know, I would expect that's probably a higher effort if you're going for an approach that might be more common, which is that you kind of develop your architecture and your spec, and then you do some testing right off the bat. And then after you use that to kind of have a little bit more assurance about your specification and your code, then you would more likely then at that step go through the verification process. But a nice thing with this is that now I didn't have to do any of that function mocking and stubbing. That's all done for you by HAMR. And with my effort, I usually get about 100% code coverage. However, because it's randomized, I don't always get 100. I could probably tweak the number of tests or tweak some of the weightings to get more consistency, but it didn't feel especially useful at the time to continue working on that. I'll also note that having all tests passing currently does not mean that all contracts are being met. And having all tests passing plus 100% code coverage still doesn't mean all contracts are being met. This is mainly because the way that the tests are generated is it's saying if requirement 1 or requirement 2 or requirement 3, then test pass, right? Which means I actually get 100% of my test passing if I don't coerce my data at all, because it's basically always going to create malformed packets, which will always trip my contract that says, hey, don't pass through malformed packets. So, you know, I've talked to KSU about that, and they're looking at ways to kind of show, like, I think an untested contract should look like a failure case when running your tests. But all of this provides like a nice method to test out your specification and your code. And it could be used on its own, especially for just gaining some initial confidence, especially for people who don't have verification expertise. But it can also be used with verification to increase confidence. And just a little example of kind of the property-based library that we're using. You come up with these strategies to kind of define input data. I think it's a little bit more obvious when you're using structured input. It's quite a bit easier to just say, like, oh, you know, do some weighting for variance of an enum or something, right? With an array, it's a little bit more complicated, but essentially what you're doing is composing different items together, different strategies, and then kind of working off of what gets generated. So as an example, looking at like an IPv4 packet, first we need to define the protocol based off the strategy. And so, you know, these are all of the valid protocols we can have. We care about TCP and UDP happening more often because we want to see, you know, nested success cases, right? And then, you know, there's the occasional one that's just going to be random data that will end up looking like a malformed packet. And then once we've, you know, generated that piece, then we can kind of figure out, okay, if it's TCP, then we also need a TCP strategy. If it's UDP, we need a UDP strategy. And then you can kind of compose those together. So we pass in the IPv4 length strategy, the protocol packet strategy, and then a randomized vector of bytes. And then we can kind of construct that. So here I need to copy in the generated random length at the specific location in the frame and set the protocol byte at the specific location, and then splice in the protocol packet in a specific location. And here, looking at the length strategy, you can see most of the time I just create a valid length, and then occasionally I create an invalid length. And yeah, it's basically just more of the same for this UDP strategy, right, where it needs to generate a port value. And so like a fifth of the time we create the valid port that we want to see, and then the rest of the time it's just a random U16. So I think in conclusion, by layering our security strategies, we can increase confidence and make the subsequent strategies easier. The use of the inspected tools, such as HAMR and Varus, can make formal methods more approachable to system engineers and can improve both development time and testing time and verification time. The modeling workflow that it provides allows for formalization of requirements to the architectural contracts. It provides a nice generation of our infrastructure and architectural code that glues the different components together. And then it also generates the verification contracts and spec functions and our test infrastructure. It gives us a nice separation between architecture responsibilities and the application development responsibilities. And it also provides really nice reconfiguration and reuse of components. And we can already start to see that by seeing how simple just the policy implementation of the firewalls were when they're using the same shared library. And then it gives us really nice, obvious traceability from requirements to contracts to our verifications and tests. And kind of some of our next steps, we would like to continue to apply this approach to the low-level Ethernet driver and to further applications. We'd like to see, what does it take if you have a requirement change on one of your firewalls? What does it take when you insert a new component into the system? And kind of just continue getting metrics on, how much effort are we saving with these tools? And that's all.
Great. Any questions?
So your firewall seems to be stateless, and RX and TX are completely separate. Have you thought about making it stateful, for example, to be able to track TCP connections or defend against something like TCP, SYN, packet flooding, anything like this? And how realistic or how much effort would it be to do something like this?
Yeah, that's a good question. I haven't really considered it, though I do know the tools have some methods to keep track of state and do that. There's already some state being tracked in the generated code, so it would be just kind of applying the same methodology to do that. Currently, that's not really on my roadmap, but it is interesting.
Were you assuming that the NIC was not going to be doing most of these things, or were you assuming it was actually capturing most of the things and throwing them away, and you were just looking for elegantly designed bad packets?
Yes, I guess really by checking for malformed packets myself, I don't have to trust the NIC to do it, which I think is nicer and makes it more general, especially because some of the messages are coming from the VM, and also if you look at it at a general case, you could hook it up really to any component, and the idea would be, do you trust that component to have already done any parsing on the packet or not? So I think it just gives us more flexibility at where it can be used.
Thanks, it was a nice talk, thank you. So I like the traceability aspect of this work a lot, and I was wondering, so the requirements you showed, the high-level requirements in the, not SysMLv2, but ADL, I guess, they seem somewhat still like a little bit low level. I was wondering whether you thought about, or whether the project has thought about whether those requirements could be used to prove system level properties, like some component, if it receives a packet, it's always a UDP packet, or whatever the higher level properties that are implied by the requirements are. It would be nice to be able to sort of link those formally to the lower level proofs that you're doing here. I don't know.
Yeah, definitely. That's probably something John could expand on more, but that's like. We can prototype some things like that now.
Oh, cool. Yeah.
So also utilizing the existing agree framework. Yeah. Yeah. So this is part of the hierarchical verification strategy, where we have properties that we're verifying at the system architecture model.
Right.
Independent of the implementation, and then those contracts are allocated to components then for implementation and verification using Verus.
No, that makes sense. I like this strategy a lot. Yep. Thank you.
Thank you.
So just out of curiosity, so for Verus, how long does it take for you to verify, say, one component, say the parser library? Because you mentioned that there are some difficulties with bit shifting. Is there cases where you change a little bit in your code and then you have to wait for Verus to run the verification process for, I don't know, a few hours again?
Oh, no, Verus is quite performant, so I'd never really had any issues. There was one point where I was attempting to see if I could use a spec function that was implemented from the contracts in place of a spec function that I wrote in the shared library. And it had trouble equating those, and it took a while and then exploded. So I gave up on that. But other than that one case, it kind of just handled everything well. But like, yeah, bit shifting, it just failed to verify. So I had to modify the code to do like anding and whatnot, and then it worked fine.
Cool.
In addition.
Let's thank Robbie again.